question. So there's a couple different questions, like questions 16 and 17. Let me do 17. I mean, they are basically the same thing because both of them amount to having to know the formula for the capacitance of the vacuum parallel plate capacitor. And there's a derivation done in the textbook. Let me first write down on the side to see if I remember this. I have a couple different versions memorized. The version I have memorized is the one that I have memorized forever. It's the capacitance of the parallel plate capacitors is the area times permittivity of free space over D. I think that's right. Or in terms of Coulomb constant, which I encourage you to try using, this is 1 over 4 pi, or more precisely, Coulomb constant is 1 over 4 pi epsilon naught. So the epsilon naught is 1 over 4 pi times Coulomb constant. So this should be A divided by 4 pi Coulomb constant times D. So I think that's the formula. Let me look it up just to be sure that I don't know, didn't forget it or something. So in this section, you will see the capacitance of parallel plate capacitors derived. They go through all the consideration, derivation, and when they have done that here in this section, what they will end up with is this. Capacitance is area times permittivity of free space divided by D. So that's the formula. And starting from there, then the rest of the question is relatively simple. They are giving you the capacitance, and they are giving you one of the two geometric quantities. In one question, it's area. In this question, it's the separation between the two plates. And then you solve for the remaining quantity. So for this expression here, for this question, I want to solve this for area. I'm going to take this and solve it for area. Then area is equal to 4 pi Coulomb constant times D times the capacitance. So that's it. Just plug in the numbers and we should be done. I'm just going to use Wolfram alpha to plug in numbers, mainly so that I don't have to look up Coulomb constant. Such an hassle to look them up. 4 pi times Coulomb constant times, and I'm going to let Wolfram alpha do all the unit conversions. So 2 millimeter times capacitance, 6 picofarad. And it'll give me the answer in a bunch of different units. And I hope one of them is in the unit of, well, something like a centimeter squared. It might be, so square meter, that's one of them. There it is, square centimeters, 13.6. So, yeah, that's it. It's a relatively simple application of formula. And I think this formula is useful not so much for actually calculating capacitance. Very often, when we have capacitors in practical circumstances, we measure them. We don't compute their capacitance based on some theory. Because with the practical capacitors, they often contain dielectric as well. And the area and the separation parameter is not something you can easily measure. What this is useful for is for giving you the dependence on how the arrangement changes. So, in this expression, you can see that capacitance is proportional to the area of the capacitor. I think I've done a lecture of that. And it's inversely proportional to the separation between them. I've done a lecture on that too. And when you internalize what this means, it'll help you understand how to combine different capacitors. So you could combine capacitors in series. That's one way of combining them. Or you could combine capacitors in parallel. That's another way of combining them. And one of the things that understanding of this expression for capacitance of parallel plates will help you understand how imagine we are dealing with the identical capacitors, so both having the same capacitance. Then in this arrangement where you've placed them in series, this is as though you are taking a separation D for a single capacitor and changing that to 2D, 1D, and 2D, as though. And you can see how when you replace the D here with the 2D, then capacitance, it goes down by a factor of 2. And that's what you should expect here. And here you can imagine the same thing, how if you have two capacitors connected in parallel of the same areas, then having two of them is as though you have a single capacitor of area 2A. And you can see here how doubling the area will double the capacitance. And later on, we are going to deal more properly with the combination of capacitors in these combinations. But one way to get intuitive understanding of how that works is through understanding of this derived formula for one of the simplest arrangements you can get. Okay, I think there's enough time for one more question. Let me see what question I'll do. So this, I've done a version of that already. Oh, I think this question I give enough a hint. Yeah, I already tell you example 8.3 might be particularly relevant. So I'll tell you why that's relevant. When you scroll down to example 8.3, spherical capacitor. So the arrangement is something like this, but starting from this description, you can figure out the capacitance of an isolated sphere. It's kind of a bit unusual because usually when we deal with the capacitors, we are dealing with the two conductors. An isolated sphere would be a single sole conductor. And this example is how they are calculating capacitance of that isolated sphere. The way they are doing it is they're taking the capacitance that's derived for this setting here in 8.4, and then they are taking the limit as this radius R2 goes to infinity. So when you do that, so as in the limit R2 goes to infinity, so that outer shell is infinitely large, then you get this answer. Taking the limit of, oh wait, they say compare it with. I just did that to get the capacitance, but you get the same result. When you take the here, when you take the limit as R2 goes to infinity, then this is kind of the reasoning process you go through when you consider the limit as R2 goes to infinity. So you're looking at the term here. On the numerator, I can't really do anything because R1 is multiplying to something that's going to infinity. So both of these are significant. I can ignore any one. Now these two are adding or subtracting. In this kind of relationship, as R2 goes to infinity, R1 is basically negligible. It's not important. So I can say this goes to 0, or I can neglect it. Once I've done that, you can see that R2 cancels out here. So you end up with a 4 pi epsilon naught R1. And that is the capacitance of a single spherical conductor. Or I guess in terms of the units I'm asking you to consider using is R1 divided by Coulomb constant. So, oh, I guess I've almost done this question, so let's just finish it. So this question, using that expression, will be you take the radius of Earth. So let me just plug those in. I have my radius of Earth, divided by Coulomb constant, and that should radius of Earth equatorial radius per, yeah, that's right. And yeah, one of these units is in farad. So conventional farads. Okay, I'll do 7.0, so 7.10 times 10 to the minus 4 farad. 7.10 times 10 to the power of minus 4 farad. So yeah, Earth is a capacitor and it has some finite capacitance. And also, is the Earth? I think the ground of the Earth is on net electrically charged. The Earth has a bit of a charge separation that's between the ground and the air above.